Okay, Assalamualaikum and good afternoon. So today we will proceed, we will continue our lecture on stress and strain under axial loading. Okay, so in previous lecture we look on a material under axial load, and then I also already discussed a few examples how to calculate the normal stress under axial load. Okay, so where the normal stress, which represent by the sigma, okay, is equal to P over A, where P is the internal axial load and A is the cross-section area. So due to the axial load, so the material will be subjected to the normal stress, and again the normal stress sigma is given by P over A. And then for today's lecture, we are going to see how to calculate the normal strain. Okay, normal strain due to the axial load. Okay, what is the strain? Strain is the quantity that we will employ to quantify the deformation of the material. Okay, under axial load. So the strain, okay, is represented by the epsilon. Okay, so the symbol epsilon here. Okay, so the symbol epsilon. Okay, let me get my pen. Okay, the symbol epsilon here, and it represent the normal strain. Okay, so the normal strain is given by the delta over L, where the delta is the elongation. Okay, delta is the elongation. Okay, elongation of the material. Okay, divided by the L. L is the original length. Okay, so for today's lecture we are going to look at on how to calculate the normal stress due to axial load. Okay, I skip this one. Okay, so if you look at here, when we have, let's say we have bar, okay, bar, and then the bar is subjected to load P. Okay, so let's say before that, let's say we have a bar, okay, with the length of L, okay, with the length of L. So the L is the original length of the bar, and then the bar is subjected to load P. Okay, the same bar here is subjected to the load P. So what happens is the bar will deform. Okay, will deform with certain value of elongation. Okay, let's say this is the elongation. Okay, elongation of the bar when it is subjected to the load P. Okay, so this is let's say delta over 2, and then this is another delta over 2. Okay, so the total length, okay, now the total length after the bar is subjected to load P is equal to the L plus delta over 2 plus delta over 2, which is equal to L plus delta. Okay, delta. So this delta is the elongation or the deformation of the material when it is subjected to the load P. Okay, so here the value of the delta, okay, can be positive or negative. Okay, so if the bar become longer due to the load P, okay, let's say we have a bar and then subjected to the load P, and then when it is subjected to the load P, the bar become longer, so that's what we call as a positive deformation. Okay, however, if the P cause the bar to become shorter, so that's what we call as a minus delta. So we say that the deformation of the delta is negative. Okay, so this is the case when the bar become shorter when subjected to the load P. Okay, so as previously shown, okay, the strain or epsilon, okay, is given by the symbol epsilon, is given by delta over L. Okay, so delta can be negative or positive. If the material becomes shorter, and then we put minus delta. If the material become longer, okay, due to the load P, so the delta will be positive. Alright, so now let's look at on what is the tension and compression test. Okay, so tension and compression test is an important test. Okay, as an engineer, you have to know how to perform this test, and also what is the properties, what is the values that we can obtain from this test. Okay, so basically the tension and compression test is performed in order to investigate the ability of the material to sustain a load. Okay, a load. Alright, so the figure here, okay, shows the typical machine, okay, the machine, conventional machine, to perform the tension and also compression test. Alright, so so now if you look at here, okay, so this is the typical stress strain curve or stress strain diagram. Okay, so this curve is obtained after the tensile test. Okay, so if you have for example, if you have the material, okay, the material ductile material, if you have ductile material, for example here, so you have the specimen that made from ductile material, and then you perform the tensile test where you given the load to the specimen, and then at the end of the test, so this is the common stress strain diagram that you will obtain. Okay, so if you look at here, there are two different regions here. The first one is the linear line, okay, linear line or linear deformation. Okay, and then after y point y, okay, we call it as point y here. So you can see that the deformation is no longer linear. Okay, here the deformation is linear, and then up to, okay, after the when the deformation exceed the y point, okay, point y, and then the deformation become non-linear. Okay, so this linear line, okay, this linear line, we call it as a elastic region. Okay, so it means that the here will be the from the starting point 0 to point y, so is we call it as a elastic region. Okay, and then after y point y up to the fracture point, okay, fracture point, this is what we call it as a plastic region. Okay, so the plastic region where plastic region is identified when the deformation become non-linear. Okay, and then if you look at here also up to point y, okay, you can see that the material deform uniformly. Okay, and then after, okay, after y point, okay, up to the yield UTS point, okay, UTS point here. Okay, so you can see that the elongation of the material is still uniform. Okay, it's still uniform. But after UTS point onwards, okay, up to the fracture, we can see that the material, we can see that the necking happened on the material. Okay, what's the necking? Okay, so that's the what we call as a necking, or in some textbook. Okay, necking also is known as a tensile instability phenomena. Alright. Okay, so that is the definition for what happened when we apply the load, tensile load on the sample. Okay, I will explain in detail here. Okay, so let's say I draw the shear stress diagram. Okay, stress strain diagram. Sorry, stress strain diagram, and then this is the typical curve that you will obtain. Okay, so similar to the to this curve. Okay. Alright, so as I said, there are straight line here. Okay, there is a straight line here. Okay, this is what we call as a linear deformation. Okay, and then so how to determine the point y? Okay, how to determine the point y? So we will apply the concept of 0.2% offset line. So if you draw 0.2%, okay, strain, okay, and then draw the linear parallel line, okay, parallel line to this line, okay, parallel to this line. Okay, you will get something like this. Okay, alright, so this is the linear line. If you draw the linear line, okay, from the 0.2% offset, so and then up to the curve, stress strain curve, and then this is what we call as a point y. Okay, point y, and point y, the stress at point y is called as a yield stress. Okay, so this is the yield stress. Okay, point y, okay, the stress at point y is called as a yield stress. Yield stress. And then the maximum stress, okay, the maximum stress from this curve is called it as a sigma ultimate tensile strength. UTS is the short form for ultimate tensile stress. Okay, so that is the maximum stress that can be supported by the material. Okay, and then the stress at fracture point. So this is the fracture point. Okay, fracture point, and the stress at fracture point is represented by sigma f. Okay, fracture of failure point. Alright, and then this line. Okay, another important part here is at the linear line. This linear line. Okay, this linear line, okay, can be represented mathematically by sigma equal to E epsilon. Okay, so how to get this relationship? Okay, how to get here? So if you look at this line, okay, let me draw again. Okay, let's say I draw the linear line here, this one. Okay, I draw here. So this slope, okay, is represented by E. Okay, what is the E? E is the Young modulus. So this is another curve. So let's see. Okay, from this figure we can see that the y-axis is represented by sigma and x-axis is represented by the epsilon. Okay, so how do we determine the slope of this line? Okay, the slope is given by y over x. Okay, y over x, and for this case the y is the sigma and then the x is the epsilon. So we can write that the E, which is the Young modulus or the slope, okay, is equal to the sigma over epsilon. So we can rewrite this equation. The sigma is equal to the E epsilon. So this is a very important equation that we will apply in the next lecture. All right. All right. So there are two type of, for information, there are two type of engineering material. The first one is the ductile material, and the second one is the brittle material. Okay, so the curve that I show you in the previous slide, okay, it looks like this. Okay, so this is basically is for ductile. This is the stress strain curve or stress strain diagram for ductile material. Okay, however, for the brittle material, if you conduct the tensile test, okay, for the ductile material, okay, you can see that the curve is look like this. Okay, look like this. So what is the difference between the stress strain curve for ductile material and also brittle material? Okay, so ductile material that can subjected to large strain before it rupture is called ductile material. So for the ductile material, we can see that the strain, okay, the strain which is here from here to here, the total strain is large. Okay, it's large. Okay, and then for the brittle material, we can see that material that have little or no yielding before failure. So the strain, okay, the strain is smaller. Okay, the strain is smaller compared to the ductile material. And also brittle material normally has no plastic region. Okay, we can see here this is the straight line, basically. Okay, so here is the elastic region, and from here to here is the plastic region. But for brittle material, okay, so normally the plastic region is very small, but and sometimes there is no plastic region. So that is the difference between stress strain diagram for the ductile material and also stress and strain for the brittle material. So I hope you can differentiate between these two stress strain diagram. Okay, now let's proceed with the deformation under axial loading. Okay, so we have looked at from the previous lecture or the previous slide, the slope, okay, the slope of the stress strain curve, okay, which is here. Okay, the slope here E, okay, can be represented by the E is equal to, this is the stress, this is the strain, so stress versus over the strain, and then we can rewrite that the stress is equal to E epsilon. Okay, E epsilon. So that's how we obtain the stress equal to E epsilon. And then we can rewrite, okay, this equation, okay, in terms of epsilon. Okay, so we can write in terms of epsilon. So epsilon is equal to stress over, okay, if we bring here, okay, if we leave it the strain, okay, so we can write the strain is equal to epsilon, okay, sorry, sigma over E. Okay, so this is how we get the epsilon equal to sigma over E. And then we know that, okay, and then we know that the stress is equal to P over A. Okay, so if we substitute this value into this equation, so we can write that the epsilon is equal to, so we replace the sigma by P over A, so we get P over A, okay, and then don't forget we have an E here, so you write E. Okay, so that's the equation for strain equal to P P over EA. Okay, and then we know that the epsilon is equal to delta over L. So we can write here this one is also equal to delta over L. Okay, delta over L. And finally, if we leave it, the delta alone, or we write this equation in terms of delta. So the delta is equal to, so we bring the L into this term, so we get delta equal to PL over AE. So that is the equation for deformation. Okay, so deformation of the material basically is given by PL over AE. Okay, so that is the same equation that we derive. Okay, so delta is equal to PL over AE. So that is basically the for single material that having uniform cross section. Okay, if you have the structure with multiple material or different material, and then also the cross section area for the material or the structure is different, so you can write the equation for delta deformation is equal to the summation of PI LI over AI EI. Okay, so that is the equation for variation in loading, okay, or material, and also cross section. Okay, cross section. And then if however, if the structure, okay, the structure that you are going to analyze has uniform cross section and also made from the single material, you can straight away use the equation. Okay, so now let's proceed with example. Okay, I will show you one example how to solve the deformation of the material, okay, for a given structure.